Okay, hi everyone. So I briefly mentioned to each team my feedback. Also, some of the teams were not here. I had some feedback. I wanted to talk to them specifically about their proposals, but they were not here. But feel free to contact me, and I will be happy to help. Also, so one general comment about uh, the proposals of the projects is that I also mentioned in the announcement is that whatever problem you're solving, please first explain the problem and formulate the optimization problem or problems that you're having in your project. Formulate it as what we have a lot of formulations of optimization, like right we have seen that in the course, like minimize or maximize some costs subject to these constraints. I read your proposals. All of you can write such optimization problem or problems for your uh, uh, projects. So please do that. This formulation, it encapsulates all your problem as a optimization problem, and also have the constraints and this. But before that, explain the problem. So it and also the notations and everything, and then write the optimization problem. Another thing, please explain the optimization algorithm that you are going to use, or algorithms, or that you are going to use for solving your optimization problem, and also its pros and cons, and the details of that. Also, if you when you are using one specific or several specific algorithms for solving that, please explain that algorithm briefly and how it is working and its pros and cons compared to other algorithms, and what justify why you're using these algorithms or this algorithm for your problem. Also, please report the results and experiments and try to analyze them. Just don't show the results and these are the results. The results are very helpful if you analyze them. So yeah, and also don't worry about your do your best. Don't worry about your grades. Try to enjoy your projects. As long as your projects are well enough, you will have a good mark for that. I will not compare the groups with each other. I will consider every project of every group by itself alone. And also presentations, as long as you present, I expect everyone in the team to present, have a part of the presentation, and you will get the mark for that. Don't need to worry about that. So that's the thing. Also, in your project, either in coding or your problem itself, in the mathematical aspects of it or whatever theory, if you face any problem after searching and you trying with each other, if you still need help, you can reach out to me. I will be more than happy to help you. So as I said at the start of the course, this is a course that we all are gonna learn together. I might not know something and also might learn by being in the loop. So yeah, just feel free to reach out to me if you face any problem. I'll be happy to help. That's another thing. So then also about the midterm, thank you very much. Also, I heard your feedback after the midterm. So one of you, several of you guys mentioned that. So one of the comments actually was that it was a bit lengthy. Okay, sure, I will try to make the exams shorter in the next semesters in the other courses that I'm gonna offer. So I want you to make sure to be sure. I assure you that your feedback is appreciated, and I will apply them. Okay, sure. Yeah, I will make my exams a bit shorter. They shouldn't be that much lengthy. You're right. And also, as I said, don't worry about your grades. Do your best and try to enjoy the course. I will try to be a good grader too. So that's another thing. So we talked about midterm, about the project. Any question about either the course or the project or the midterm? So one thing about the assignments, according to the timeline and what we have done so far, it seems that we are going to have another assignment, and that will be enough because we don't have enough time to have a third assignment. That's fine. And if you haven't done much good in assignment 1, don't worry. Please try your best in your assignment 2 as well as project, and you don't need to worry about your grade. The grades at the end will be curved, but again, try your best. Don't say that I don't do my best and let's see what happens. Please try your best, and you don't need to worry about it anymore. Just try to enjoy the course, but in different parts of it, like studying, doing the project, doing the assignment, etc. So that was one other thing that I wanted to tell you. Another thing is that, unfortunately, I think my tablet or Remarkable, they have apparently updated the software in a way that maybe my device is a bit old and it doesn't let me share right now. I tried a lot, but it doesn't let me share screen my tablet. That's a technical issue out of my control. Apparently, they have made such an update. That's fine. So nothing can stop us. We can try alternative things. Maybe next time I will use another tool. But for now, I can teach on the PDF and share screen the PDF and explain the details to you by speech. But you don't, and also feel free to interrupt me if you have any question. Everything clear? No any question? No? Okay. By the way, why are we only 10 here? Where are the other ones? Don't know that? Okay. Another thing, by the way, if the department, as I said in the announcement, if the department agrees, I will be probably teaching 2 other courses in the next semester. One of them is deep learning, and the other one is statistical machine learning, if the department accepts that. And feel free to take those, and we'll have a lot of fun, I think, in those courses. Currently, they are full, but as far as I know, there's a high probability that the department will increase the capacity. So if you haven't taken those courses and you want to take them, take a look at the course regularly. They will probably open the capacity. So that's another thing. And deep learning is about deep learning, different various algorithms in deep learning. We are gonna cover very different algorithms, from fundamental ones to the state-of-the-art ones. So we start from neural networks, and at the end we'll also cover very state-of-the-art algorithms such as diffusion models and generative models and all of those. Also in natural language processing, for example, attention mechanism transformers and all of those areas. So they are useful in different applications. From no matter which background you are from, I think deep learning can be useful for you. The other course is statistical machine learning. I think that is also a very important course. I think both are equally important. And statistical machine learning is almost all machine learning minus deep learning, and that's a huge area. It's a huge area. Don't think that machine learning is all only deep learning. No, it has a lot of things, statistical approaches. Such as Bayesian models or variational models or classic classification and regression models, SVM, FDA, LDA, QDA, and also probabilistic models, probabilistic graphical models, hidden Markov model, HMM, and all of those areas. Also physics-based models such as energy-based models, such as Ising model and all of those areas, factor graphs. There are many areas that we are going to cover. So from fundamental to state of the art. And so I think both courses are important, either in industry or in academia. In both areas, they will be very useful. And please let your friends also know about these courses. And I hope that I see you there. And the courses will be in person, by the way, and we'll have a lot of fun together. So, yeah, any question? No? Okay. So let me share screen then.
Hello, Professor.
Hi.
Actually, I don't have doubt regarding the subject, but regarding the assignment marks, can you give us the feedback as well for those?
Are you talking about this course, the optimization
Yeah,
course, or the?
for optimization, yeah, assignment feedbacks.
So you mean you have any ambiguity about your mark for
No, no, no,
assignment?
no, not ambiguity, but where I made mistake.
Oh yeah, you can see TA's notes on your submitted PDF. Have you seen those? So
I
if
think it is not there. I checked, but
I,
I'll check
ye-
it once again, and if anything,
sure,
I'll ask you.
sure. Please check and let me know if you can't find that. But as far as I checked, I saw some notes on your PDFs, I think with blue color, or green color, or blue color. What? So yeah, and I think you can see the feedback of TA. But if you didn't understand any feedback or any feedback of him, please feel free to reach out to him. He's very responsive. He's a very good guy. And if you can ask, and if there is still ambiguity and you need you think you need me to be in the loop, please feel free to reach out to me, and I will be in the loop, and we will discuss it together, all three of us, me, you, and the TA. TA has graded you kindly, and yeah, I think the best person to reach out for your marks in this regard is TA, because he has graded you based on the solution key that I have given him. But yeah, again, if you think I need to be in the loop, please let me know. And by the way, I have also asked your TA to mark your midterm generously, so you don't need to worry much about that. But try to do your best in the rest of the semester in the assignment too, as well as your project. Any other question?
Yeah, I have a
No,
question.
thank you.
You're welcome. Alireza, you
Can
are
I
saying
ask?
something? Yes,
Yeah.
sure.
I have a question about the courses that you want to present for the next semester.
Yes.
I want to know that what majors of engineering can uh, apply for these courses. You know, for example, I am mechanical engineer and I am studying in this major. Can I, for example, apply for them?
Do you mean administratively, or are they useful for your major? Which one
No,
are
no.
you?
At first, administratively.
So you need to ask the department for that. I don't know that, but I
Uh,
assume this is my assumption. I'm not sure that people from different areas of engineering and maybe even other departments, because even as you see, optimization course is in engineering, but we have had people from CS too in this class, as far as I know. So
Sorry, I just want to let you know that there is no restriction except,
yeah,
for example, for MNG students like me, I think Alireza is another MNG student.
okay.
They just can select limited courses except their major, such as mechanical or AdaGrad. For example, I can from 9 courses that I should have to choose, I just for example 1 or 2 from general courses, 2 or 3 from my major, which are about my major, something like that. There is this restriction just.
Oh,
No.
okay. So yeah,
Just
I'm not.
ask for from your maybe graduate program assistant about this.
Yeah, so it's the best person
Thank you
to ask.
so much.
Yeah,
You're welcome.
the best person to ask about these things is your the partner, the school, and also I'm not sure if they also ask this. They may let you take additional courses, so they might have a minimum bar, but you can ask. I'm not sure. You can ask them, but regarding the fact that whether they are useful for your major or not, I think it's useful for any major. Yes, because nowadays AI and machine learning are used in different areas, right? So that's, sorry about it. That's one thing.
Thank you so
And
much for your answer.
no problem. Yeah, I'll be happy to have all of you guys in the class. I have had a lot of good times with you. So any other question before we start the course? No? Okay. So let me share screen. Again, as I said, I can't write apparently right now on the on my screen, but that's fine. So do you remember so we were talking about the gradient descent last time, and we reached to the point of momentum. But before that, let me correct one mistake that was in the slides. And it was here, equation 17. If you remember, sorry, where is it? Okay, equation 17. So it's C P transpose gradient of F xk, not F, because F of xk is scalar and P transpose F doesn't make sense. Because of this not making any sense, I went and looked it up, and I found out, okay, there is a typo here. So it's a P transpose gradient of F xk. So that was one typo that needs to be corrected. I will correct that in the slides. It was in the Armio line search or backtracking line search. So okay, now momentum. So gradient descent. Gradient descent with momentum. Gradient descent and many first order methods, they can have momentum term. And what is momentum? Momentum is we see it here. So in equation, do you remember this? Do you see my cursor, by the way, guys? Can you tell me if you can see my cursor that I'm rotating?
Yes.
Yep.
Yeah. Okay. Great. So this equation, this is just the update every step of gradient descent, right? And why do we have superscript k for delta x? Because we might have different steps, different step sizes in different iterations or different updates. So at iteration k, delta x is we can write it as alpha, a fraction of the previous delta x in the previous step, k minus 1, minus eta gradient of f. So as you see in equation 19, if you set alpha to 0, delta xk is minus eta k gradient of f xk. And if you put this equation 19 here, you will have the original gradient descent. If you set alpha to 0, then it will reduce to a gradient descent, right? Because delta, the step size is minus eta gradient of f. This is gradient descent. However, if you have alpha greater than 0 here, then you have this update. The update has another additional term, which is a fraction or a factor of the previous step size. And what does it say? So it says that I have some, how should we call it, inertia or momentum in our step size. In my update, I don't want to update to a completely new update. I want to have a history of my previous update. So my current update has an impact from the previous update. So alpha, delta x in the previous step, and then plus the term that we had in original gradient descent. Is it clear? So again, we have some additional term which makes a momentum or an inertia or a history in our update in order to have a history from the previous update in the previous iteration. So this is the momentum, the idea of momentum. And what is its impact? If you see these two figures here, without momentum, we have a lot of oscillations. When we have momentum, usually it becomes smoother, and we don't have much oscillation. And I think the idea is intuitively understandable. Why? Because when you have a log of your previous history in your update, you make it smoother. You can't change much because you have your previous history inside your current update. That's why you don't have much oscillation when you add momentum. And it has been used a lot in optimization. So gradient descent is over now. Let's talk about another first order optimization method, and that's steepest descent. Okay. Steepest descent, sometimes people in the literature confuse or use interchangeably steepest descent and gradient descent, but they are different. We'll see how they are different. So steepest descent is very similar to gradient descent, but there is a difference between them. And what is that? In the steepest descent, we move toward the negative gradient. It's the same as gradient descent. However, here is the difference. As much as possible. So in gradient descent, we don't do that. So here we go toward the negative gradient. We do it in gradient descent as well. However, here we do it as much as possible to reach the smallest function value, which can be achieved and at that iteration. So what does it mean? So here in equation 20, look at it. If you put equation 20 into this equation, and if you ignore argmin here, so let me think. Okay, yeah. Consider this equation. This is gradient descent, right? This is original gradient descent. However, if you change eta by this eta k, and eta k, so step size, you're changing the step size in a way that it's kind of an adaptive step size in the gradient descent. However, you make the step size in a way that you want to find the smallest value of the function in that direction that you're moving. So it's like you're going down a mountain, and at each iteration in gradient descent, you go just a small step, right? This is how gradient descent works. So if you can see my, can you see me too? Right? I assume you are seeing me. So when on a mountain, you are coming down step by step. This is what gradient descent is doing, right? Because minus gradient is toward the valley in the mountain. But if you go one step at a time, very small steps, this is gradient descent, and with different learning rates probably. However, if you find the learning rate or eta in a way that at every step you jump in a way that you decrease your cost function the most that you can at that iteration, that's the steepest descent. But its name is obvious. You're going in the steepest that you can on this mountain. So this is a difference. So steepest descent is similar to gradient descent. However, you find the eta or learning rate in a way that you want to make the function value the minimum at that iteration. Another way to describe steepest descent is in the last bullet point. So you can see it as you can see this. Look at this update that we have in the first order methods, and this delta x is argmin of gradient of f transpose v and y. So why is it that? So when you have f of x plus v, consider v as a direction. So f of x is the current location. F of x plus v is the function value at the next iteration, right? You can write it by first order Taylor expansion. Do you remember first order Taylor approximation? You can write this function f of x plus v approximately as f of x plus gradient of f of x transpose v. X and v are vectors, right? Gradient of f is also a vector. So you're saying that I want this to be minimized, right? This f of x plus v, because in the next iteration, I want to minimize that. Therefore, for this to be minimized, you can also minimize this gradient of f transpose v. That's why here we are minimizing gradient of f transpose v by subject with respect to v, and subject to having a small v. We don't want v to be very large. Its length we want to be less than or equal to 1. So in the hypersphere with radius less than 1, I want to find v in that hypersphere. But I think the last bullet point is a bit ambiguous. I think the previous bullet point, equation 20, is more obvious for you to understand what a steepest descent is. Okay, but they are basically saying the same thing because you're finding the most decrease in the cost function. Any question? No? Okay, so now we go to backpropagation. I think you have heard of backpropagation a lot. If you haven't heard of it, I'm gonna explain it to you here. Backpropagation is used in neural networks. What are neural networks? So neural networks or artificial neural network is trying to mimic the brain, human's brain, in a way that so you have some neurons. In human brain, you also have some neurons, right? And the neurons are connected to each other because every neuron sends some signals to another neuron. We have a lot of neurons in our brain. So in order to have an artificial intelligence, we are saying that let's mimic or imitate the brain using an artificial brain. Let's make an artificial brain or artificial neural network. So we have several layers. You can see here, for example, we have layer 1, layer 2, layer 3, layer 4, and each layer has several neurons. And in the simplest neural network structure that we have here, it's called feedforward neural network. Every neuron in a layer is connected to all neurons of the next layer. So you can see, however, the neurons in each layer are not connected to each other. So we don't have connection between this layer and this neuron and this neuron. This neuron is only connected to all neurons of the next layer. So this is what an artificial neural network is, right? And here, assume you have some input, you feed it to the network, and it will pass through all of these, and it will give you an output. You can also play around with the number of neurons in each layer. However, the number of neurons in the first layer should match the dimension of your input. And the number of neurons in the last layer should match the number of neurons in the output, right? The dimension of output. Also, you need to note that there are some weights. So these connections have some weights. And the parameters, the learnable parameters in neural network are these weights. We want to find these weights in a way that we map the input to output the best way that we want, right? So for example, I want to feed image 1 to this. If I reshape image to be a vector, and I feed it here to input, I want the output to give me the label of class 1. If I feed digit 2, I want the label to be 2 at the output layer. So let's learn the weights or optimize the weights in a way that this is done. It outputs the correct labels for the input. This is what a neural network is. And every neuron, now let's zoom to one of these neurons. It will be like this. So every neuron, as you see, has AI and as input and ZI as output. And these x's here are the weights that we are going to learn, right? So what is this? AI, what is AI? AI is just multiplying this weight to the output of this neuron. Again, multiply this weight to the output of this neuron until here. All of these connections. Multiply this weight to the output of this neuron and then sum them up. Here you can see that. This gives you AI, right? So this times this plus this times this plus this times this will give you AI. And what is ZI? ZI passes AI through a function which is usually a nonlinear function, and we call it activation function. This is just a name. You don't need to worry about it. Activate a nonlinear function, which is usually called activation function, right? And it's usually nonlinear. It might be linear too, but it's usually a nonlinear function. And why is it nonlinear? I tell you. Okay, assume that the activation functions in all of these neurons are linear. What happens? Can you tell me? Can anyone tell me what happens? Assume that all of the activation functions here are linear, or you don't put any activation function. What happens? Can you tell me your guesses? Anyone? Guys, please give me some answer. Output is linear, not necessarily. Why? Because assume your input is linear. Assume your input is a linear data. Your output will be linear also. But if your input is nonlinear, then your output will be nonlinear too, right? Even if your activations are linear. So we can't say that output will be linear. Another thing happens. So what happens is this. When you have all of your activation functions linear, the whole network collapses to a linear projection. It's like you have one layer, because all the multiplication of several layers without any nonlinearity between them is like you're saying that consider this as a matrix U1, consider this as matrix U2, consider this as matrix U3. So it will be U1 times U2 times U3. Then someone can say, okay, why don't you call U1 times U2 times U3, call it V1, and replace all of them with a one layer named V1. That's correct. However, if you have nonlinearity between them, then you can't say that. Then you can't say that because in the middle of the layer, you can't have nonlinearity. Every layer itself is a linear projection, right? Then you have some activation function. If you remove the activation functions or if you make them linear, then the whole thing becomes one layer. And also it can't capture nonlinearity. So if your data is nonlinear, then it can't handle it properly. You need to have nonlinearity in your neural network in order to handle nonlinear pattern of data. These are the reasons that we have activation functions. So sigma I is the activation function at the neuron I, okay? And xi1 means that the neuron 1 connected to xi. So assume this is neuron ith neuron. So the first neuron in the previous layer, connecting to that, the weight will be xi1. The second one will be xi2. Assume this goes to neuron j, then this weight will be xji, right? because it connects neuron I to neuron J. So I think now you know the notation of the weights and everything. Now let's move on to the next slide. Okay, here, consider the 3 neurons in 3 successive layers. Layer L, layer I, and layer J. Assume these are the neurons with AL, ZL, neuron I, AI, ZI, neuron J, AJ, ZJ. The weight connecting this to this is called XIL. The weight connecting this neuron to this neuron is called XJI, right? Okay, now we have this AI. What was it? We'd already talked about it. XAI is summation of all of these weights here times the outputs of these neurons. I'm not showing all of the neurons here, right? But I'm summing over them. So sum over L, this L might be a lot of neurons here. Sum over L, XIL, ZL. Okay. Sums over the neurons in layer L. So far clear? If anything is ambiguous, please let me know. Interrupt me, please. Okay. So now we wanna, in backpropagation, we want to reduce some error again as in optimization, because we will see in a few minutes that backpropagation is nothing but optimization. We'll see that. So we want to minimize some error. For example, in the example that I mentioned for digits, if you introduce digit 1, reshape the image of digit 1 here and input it to the network, it gives you label 2. It is an error. It says that, network, you made an error. Why did you give me 2 for input 1? If the input is digit 9, it should give me label 9. If it gives me label 8 or label 1 or label 2, this is error. I want to reduce this error so the network becomes accurate and gives me correct label for input, for corresponding inputs, right? So we have some error E, denoted by E. I want now, let's find the derivatives, because and I think so far you have understood that for optimization, you need derivative. So derivative of E with respect to XIL. Why? Why do I take derivative of error with respect to the weights? Because I want to learn the weights. My variables, my optimization variables are the weights of the network, right? My optimization variables are, therefore I'm taking derivative of error with respect to the weights, and I want to minimize that. Okay. So the derivative of E with respect to this, by the way, guys, backpropagation is nothing but gradient descent. E is equivalent to gradient descent with a slight difference. It's gradient descent plus chain rule. So again, this sentence is important. Backpropagation is nothing but gradient descent that we learned plus chain rule. So if you use gradient descent with chain rule, it becomes an algorithm named backpropagation. And why do we need chain rule? Because the weights, we have layer by layer. The weights are related to the weights of the another layer, right? Because the layers are connected to each other. You can't see every weight by itself. This weight gets the summation here again, as you see it here. Each weight is connected to other weights, and each neuron is taking the outputs of the previous neurons. Therefore, you have to use chain rule. And I think you can guess, in order to reduce this error, I can, by gradient descent, I can say, okay, XIL here. XIL, what was in gradient descent? Do you remember? XIL is XIL of previous iteration minus eta rondo or derivative, whatever. Derivative of E with respect to derivative of XIL. Do you get my point? So again, I repeat that. I'm saying I'm using the gradient descent in order to reduce error E. I'm saying that XIL is XIL of previous step minus eta, the learning rate, derivative of E with respect to XIL. This is backpropagation. However, you might say, oh, but I don't have derivative of E with respect to XIL. What if XIL is in the middle of the network? Error is at the end of the network. XIL is in the middle of the network. How can I calculate that? Okay, now chain rule comes in. Okay, let's find derivative of E with respect to XIL. How do we do that? It's derivative of E, you can write it as derivative of E with respect to AI times derivative of AI with respect to XIL, right? This is chain rule. Recall preliminaries. We talked about it, talked about chain rule. Now, okay, let's take a look at this or this. I have repeated it here. AI equals sigma L, XIL, ZL, right? Summation. Derivative of AI with respect to XIL, what is it? It's ZL. You might be wondering what happened to this summation. The summation is gone. Do you know why? Here, I think it would be easier for me to write it down. However, I don't have, my tablet doesn't work, but this is a technical issue, but that's fine. Just try to, I say it by words. So summation of XIL, ZL over L is this. XI1, Z1 plus XI2, Z2 plus XI3, Z3 until the end, right? Now I want to take derivative of AI with respect to XIL, but let L is a specific number here, right? A specific index. Assume L here is 5. So I'm taking derivative of AI with respect to XI5. What was the summation? It was XI1, Z1 plus XI2, Z2 plus XI3, Z3 plus XI4, Z4 plus XI5, Z5 plus XI6, Z6 until the end. All of those are constant with respect to XI5, except one of the terms, and that's XI5, Z5, because the other ones don't have any XI5 in them. That's why we only have Z5 as the result of derivative. So only one of the terms becoming the derivative. The other ones are constant with respect to that specific index of L, right? So I think you now understand why derivative of AI with respect to XIL for a specific L is ZL, and the summation goes away. Any question? No? Okay. Now, what are we talking? Okay. Now, so this is ZL. Derivative of E with respect to AI is derivative of E with respect to AI. Let's call it denoted by delta I. I call it delta I. Now, so this derivative of E with respect to XIL becomes delta I times ZL. Okay. Now let's continue. If layer I, assume, because we are talking about XIL, right? So this layer I is important to us. If layer I is the last layer, delta I can be computed by derivative of error with respect to the output. Why? Here, consider this, because when we are at the last layer, assume we don't have layer J after that, right? We only have layer I at the end. So I'm talking about the last layer of the network. Error is at the last layer. So the derivative of E with respect to AI is just based on the activation function, right? And the error itself. So we should see what is the error function. It might be mean squared error or any function. And we also have some activation function. Do you remember? Sigma I. So we can, because error is a function of Zi. Zi is a function of AI by sigma I, right? So again, using a simple chain rule, we can simply calculate delta I. So delta I for the last layer is just a simple derivative, right? Because its error is at the last layer. However, if we are in one of the middle layers, then we need to calculate delta I by chain rule again. So we have chain rule in chain rule. So we had chain rule in equation 22. Delta I itself needs to be calculated by chain rule. So we have nested chain rules. Okay. If I is a hidden layer means in the one of the middle layers. So hidden layer means the middle layer. Delta I is computed by chain rule as this. So delta I was defined as derivative of E with respect to AI, right? Now let's use chain rule. We can sum over J. See, J is the next layer. So sum over the neurons in the next layer. Sum over J, derivative of E with respect to AJ times derivative of AJ with respect to AI. As you see, this by chain rule becomes the derivative of E with respect to AI, right? Again, if we are in the last layer, we can't do that because we don't have any next layer. I told you how to handle that. It's a simple derivative. But if we are in the middle layer, we'll definitely have a next layer. That's why we can sum over the neurons in the next layer. Okay. Now, derivative of E with respect to AJ is delta J. Why? Because delta I was defined as derivative of E with respect to AI. Therefore, derivative of E with respect to AJ is delta J by definition, right? We also have derivative of AJ with respect to AI. Now we need to calculate derivative of AJ with respect to AI. Another chain rule. So we have 3 nested chain rules inside each other. One chain rule in equation 22, one chain rule in equation 23. This term also needs to be calculated by chain rule in equation 24. Now, what is this? Derivative of AJ with respect to AI. We can write it as derivative of AJ with respect to ZI times derivative of ZI with respect to AI. What was ZI? It was the output of activation function. Do you remember? Here. So ZI is here. ZI is here. See in the figure? I'm showing it here in the figure. We also have AI here. So ZI is sigma I ZI, right? Sigma is the activation function. So simply, derivative of ZI with respect to AI is sigma prime. By sigma prime, I mean the derivative of sigma. Derivative of sigma with respect to AI is sigma prime AI. It's simply calculated because activation function is a known nonlinear function, such as tangent hyperbolic, hyperbolic tangent, or it might be softmax, or it might be sigmoid function. So there are some nonlinear activation functions. These are just names. You can look them up. So it's a known activation function. It's a known function. You can simply take derivative. So this is done. Now this term, let's calculate this. Derivative of AJ, where is it? In the figure. Always look at the figure in order to illustrate what I'm talking about. So derivative of AJ with respect to ZI. AJ is connected to ZI by XJI. So we know that AJ, what is it? Here, I have written it here. Look at the cursor. AJ equals sigma I XJI ZI, right? We already talked about it. AJ equals these weights times the outputs of these neurons and sum over all the neurons in layer I. This is exactly what we have done here. Now, derivative of AJ with respect to ZI becomes XJI, and the summation goes away for the same reason that I talked about minutes ago, right? So we have XJI for this term. This term is also sigma prime AI. Now it's done. By the way, let's put equation 24 inside equation 23. So delta I becomes this. So what was this? This is replaced by this XJI sigma prime AI. However, sigma prime AI that doesn't depend on index J, therefore it can come out of the summation over J. Therefore, it comes behind the summation, and we have delta J XJI inside the summation. So we could find delta I. We could find delta I now. Let's put it back in equation 22, right? So now it means that we have derivative of error with respect to every single weight in the neural network, right? We already talked about it. Equation 22 can be used for every single weight in the neural network, from the first layer to the last layer, or from the last layer to the first layer, right? By chain rule, we could find the derivative of error with respect to all of the optimization variables. So we can now simply use gradient descent. Simply use gradient descent. How? Here. We have talked. This is the formula of gradient descent. And we have this. Do you remember? This was learning rate. I think you have heard of learning rate in neural networks a lot. This is exactly what we have in gradient descent. We might have adaptive learning rate, as we talked about in the previous session, right? Okay, so again, backpropagation, it was proposed in 1986. It changed the whole idea of artificial intelligence, AI. It was proposed by Hinton et al. It was a very good breakthrough, and it's nothing but gradient descent and chain rule. It's very interesting. Okay, any questions so far? Everything clear? Can you please give me feedback?
Yes.
Yeah. Okay, great. So now we have talked about backpropagation. Let's talk about another first order optimization method, and that's accelerated gradient method. So we had gradient descent in the previous century, but it was shown in the literature that gradient descent is not optimal in convergence rate. It means that it's not fast enough. It's slow a bit, and it shocked everyone in the world of optimization. So there was a mathematical proof showing that it's not optimal in its pacing, in its speed of convergence. So a scientist named Nesterov proposed accelerated gradient method, or AGM in short, in 1983. By the way, Nesterov is a scientist in optimization, and he is very famous for his many algorithms especially has worked a lot in first order optimization. And especially he tried to accelerate the first order methods, right? Such as this accelerated gradient method. He proposed it in 1983. Why? He wanted to make the convergence rate of gradient descent optimal. What do I mean by convergence rate? It means how fast we can find the optimal solution. When the convergence rate is high, it means that we can reach the optimal solution very fast. But if it's low, it means that we are very slow in progress. Okay, he proposed this, and he proved that this is optimal. This is optimal convergence rate for the first order method. How did that? Okay, AGM is also called, there are other names for this algorithm. Nesterov's accelerated gradient method. It's also called fast gradient method, FGM. And you can see a series of his papers which improved AGM in the references. Okay, what is AGM? It's this. Consider a sequence of gamma k. By the way, k here denotes the iteration index, right? So, and it starts with 0. So 0 is the initial random solution, random point that we choose, and then we move from that point toward the optimal solution, right? So k is the iteration. Assume we are at the iteration k, okay? We need to find, in this algorithm, we need to have a sequence gamma k which satisfies equation 26. So every gamma k, so every iteration has some gamma. Every gamma k should be a number between 0 and 1, a scalar number between 0 and 1, including 0 and 1. And for all of the iterations, we need to have this inequality. We can have different different examples for satisfying this. One of the examples is this. I've shown it here. So assume at the iteration 0, 1, 2, 3, in all of these iterations, we set gamma to be 0. However, from iteration 4 to the end, we always have iteration gamma k equals 2 over k. So if it is iteration 4, we have 2 over 4, which is half. If it is iteration 5, it's 2 divided by 5. 6, 2 divided by 6, and so on. And if you put this in this inequality, you will see that it satisfies equation 26. For example, let's consider equation first, equation 0. It's iteration 0, sorry. So we have, this is product, right? This is product. Product of 1 minus gamma 0. Gamma 0 is 0. So 1 minus 0. And we don't have other terms. So it's the left-hand side is 1. The right-hand side is also gamma 0 is 0. So 1 is greater than or equal to 0. That's correct. Iteration 1 is 1 minus 0 times 1 minus 0 in the left-hand side. So we have 1. Right-hand side, we have gamma 1 squared. Gamma 1 is 0, so it's 0. So again, 1 is greater than or equal to 0. Let's go to iteration 4, for example. So we have, for all of these terms, until iteration 3, we have 1 minus 0. So 1 minus 0 times 1 minus 0. So it is 1. For iteration 4, we have 1 minus half, because this becomes half. 1 minus half, which is half. So 1 times half is at the left-hand side. So it's half. Left-hand side is half. Right-hand side is gamma 4 squared. Gamma 4 is half. Half squared is 1 over 4. So left-hand side was 1 over 2. 1 over 2 is greater than or equal to 1 over 4. That's correct. So as you see, this sequence satisfies this inequality. And you might be wondering, where did this inequality come from? It comes from the proof of this algorithm that Nesterov proposed. Because in order to show the convergence rate, he found out that he needs to satisfy this inequality. Okay. Now the AGM updates the solution iteratively as this, equation 27 and 28. Do you remember in gradient descent, we had only one equation per iteration. However, in accelerated gradient method, we have 2 iterations per iteration, 2 equations per iteration, right? So we have 2 variables now. In gradient descent, we only have one, we have x. But now in AGM, we have an additional variable named y. So we have x and y. It's like this. Equation 27 says that let's update the next x as the previous y minus eta gradient of f at previous y. So gradient of f at previous y with some layering rate. This reminds you of gradient descent, but we also have yk here, and this is also with gradient in yk. And in equation 28, when you found this x, you put the updated x here and the previous x here. So previous x here, updated x here. Now you have a linear combination of them. See, the updated y is a linear combination of the updated x and the previous x. And as you see, it might remind you, because we see this linear combination a lot in optimization, it might remind you, do you remember in the definition of convex set, we also had a linear combination with t or alpha between 0 and 1, something like that. It reminds you of that. So we have equation 27 and 28. Together, you go until convergence. This is AGM. We can see that, okay, consider if the function is convex and differentiable with domain D, okay, and let its gradients be L smooth. Equation 2, recall equation 2. Do you remember equation 2? Let me briefly show you. Equation 2, what was it? It's this. Corollary of fundamental theorem of calculus. We said that we assume that the gradient of function is L smooth, right? Absolute value of gradient of f of x minus f gradient of f of y is less than or equal to L. This is a definition of L smoothness for gradient for all x and y in D. Now, if we satisfy equation 2, and also assume that f star is the minimum of cost function that we want to find, and x star is the solution of optimization problem, which is the minimizer. Now we also start from x0. After t iterations or k iterations, whatever, here t or k, I use it interchangeably. It denotes the iteration. Okay. Convergence rate of gradient descent can be proved. I don't bring the proof here because it becomes complicated. Just accept from me that the convergence rate of gradient descent becomes equation 29. And what is it? I will explain it to you. And also convergence rate of AGM is equation 30. Now we are going to compare these two, and you will see that AGM has a faster convergence rate. But let's first talk about equation 29. What is the left-hand side here? It says that the difference of f minus f star. Of course, it's positive. It's a non-negative value because f star is the minimum value and f is greater than or equal to f star. We know that because f star is the minimum of f. So left-hand side is always non-negative. It's either positive or 0. At when is it 0? When we reach the optimum, right? And this left-hand side shows the distance of the function value to the optimum function value. So this is showing the convergence rate because if it's showing us with what rate are we getting close to the optimal value of the function, or are we reducing the gap between the current function value and the optimal function value. Okay, what is right-hand side? Consider this. It says it's 2 times L. L is the Lipschitz constant in Y because we said gradient is L smooth. Okay. And we also have this. What is this? This is a squared L2 norm or a squared distance, a squared Euclidean distance between x0 and x star. What does it mean? It means the distance between the first initial point that we started with and the optimal point, x star. What is in the denominator? It is t plus 1. T is the iteration index. If we consider L and X as constants, we'll see that this is of the order, complexity order. This is big O notation. Complexity of order of 1 over t. It means that it grows with 1 over t. When you grow t, the rate grows with 1 over t rate. Okay, but let me tell you why intuitively why it makes sense to have this. Okay, why is x distance of x0 and x star in the numerator? Can anyone tell me? Can you please tell me? Okay, I tell you as a hint. So the first question, I answer it myself. So x0, if we start with in a way that we are very far from the x star, of course we will reach to the optimal solution very late. So it will increase. It will increase the time that we reach the optimal solution. This is kind of a time. How much time we have to reach the optimal solution. When we start very far from the optimal solution, it increases. However, if we by chance we start very close to the optimal solution, this distance becomes close to 0. So we are faster. All right. And why is also L in the numerator? It's because, do you remember when L is high, if f is the function is L smooth, it means that its slope is very high when L was high. Do you remember when we were talking about Lipschitz continuity? When L is high, look at my hand. It's like this. It's very slope is sharp. And now gradient is L smooth, which is worse. Now we are talking about the slope of gradient. It means that when L is high, it means that the problem is very hard. The optimization problem is very hard. That's why we don't want like L to be very high. That's why it's in numerator. If L is small, then will be faster. Will be reach the optimal solution faster. Also, T is in the numerator. It's in the denominator. Sorry. So that's the explanation of 29. Now we have similar thing in equation 30, but we have a squared T in the denominator. It means that, oh, it converges to the solution much faster. Again, consider T to be iteration index. Assume iteration 10, okay? In equation 29, which is for gradient descent, simple gradient descent, it means that after 10 iterations of the order of 1 over 10, we have reached to the solution. Our speed is 1 over 10. Our distance between F and F star is 1 over 10. However, in AGM, accelerated gradient method, when T is 10, it is almost 1 over 100. It means that it's much smaller. It means the distance has become much smaller. So it means that we have we have got closer to the solution much faster, because the gap is 1 over 100, which is much smaller number. Do you understand? Is it clear? What's the difference between 29 and 20? You can see that it's much faster. The gap reduces much faster than gradient method. By the way, why do we call it gradient method? Why don't they call it accelerated gradient descent? Because it's not descent anymore. Gradient descent is what we have in gradient descent. When we change it, it's not a gradient descent algorithm. We can call it a gradient method because it's using gradient. That's why they call it accelerated gradient method, not accelerated gradient descent. Okay. So far clear? Can you please give me feedback?
Yes, sure.
Clear. Okay, now it's to 8:20. Let's have a break and come back at 8:35. I will continue with the first order methods. And I think in this session we'll see we'll also code a bit of neural networks, and we'll see that it's interesting. Okay, so see you at 8:35. Okay, let me share screen. In the meantime, I tried to fix the tablet issue, but it didn't work again. But that's fine. We'll continue on this. I tried to figure out some other way to write on tablet, maybe use another tablet or something. I'll try that for the next time. Okay, so now we are in stochastic gradient methods. So a group of first order algorithms for optimization is a stochastic gradient method. And so consider that we have n data points, and let these data points be AI, each of which is d-dimensional, and we have some labels, okay? We have some cost function f, so it can be decomposed in a summation of n terms. What I want to say that assume that your cost function is a summation of n terms. And each term is fi, okay? And we are gonna see that a lot in this category of first order methods. So we have a bunch of fi's. Some examples are this: least squares error, for example. So we have some labels for especially you see this a lot in machine learning. You have some input, like some image or something, you reshaped image, I mean, and so you have some labels, like images of digits, and you have some labels, right? Whether it's digit 1, digit 2, or something. And least squares error says that, okay, assume my learning parameters, my optimization variables are X. My inputs are AI. So we have AI transpose X, and minus Li. It can be any other loss function. These are just examples, right? The important thing here is that assume that your cost function is a summation of some Fi's. These are some examples. And you have AI transpose X minus Li. By the way, here this formulation is like a neural network with one layer without an activation function. It's linear projection, and then you compare with some label. And this half is because we have 2, and when you take derivative, we want the 2 in derivative be cancelled out. That's fine. We also might have absolute error. These are some examples. We can have hinge loss like this. This is the definition of hinge loss. We want this to be a non-negative loss. Therefore, we take maximum of 0 and this. And we are assuming that the labels are either -1 or 1. Assume it's a binary classification. It's either -1 or 1, either in this class or the other class. We might have also logistic loss. Okay, these are some examples. But the important thing is that equation 31, we have the optimization problem like this. We have a summation of over Fi's, I from 1 to n, some Fi's, and we might have some scale normalization factor 1 over n2, doesn't matter. Okay, now the full gradient, it becomes this, right? Because you can take the derivative of summation of Fi's is summation of derivative of Fi's, right? Because its derivative is a linear operator. So you have this. This is the derivative of F. Now, equation 9 in gradient descent. Do you remember gradient descent? We had minus eta gradient of F, but eta was a relaxation of a step size. If we don't relax that, before that the step size was 1 over L. So we have -1 over L gradient of F, and this gradient of F now becomes the summation of gradient of F, and we also have 1 over n normalization factor behind it. So it becomes this. So if we use gradient descent. Now there is a problem. There is a problem with having this gradient as a summation of all gradients of Fi's, is that it is time consuming, especially when we have a large n. If we have a lot of Fi's, then if n is huge, then calculation of this gradient becomes time consuming and even very hard, very difficult, because at least you need a for loop in order, and in each loop you need to calculate the gradient of Fi. What if the calculation of each of the gradients be very hard? Then you have n of them, right? So a serious issue happens with gradient descent when we have a huge n here. We have a huge number of Fi's. Therefore, in this case, we can use a stochastic gradient descent, or SGD. And why is it called a stochastic? Because it has an stochastic approach. It's random. I'll tell you why. Stochastic means a random, right? So it says that let's approximate gradient descent stochastically, and let's sample one of the points at every iteration. So rather than considering all of the n points, let's only consider all of the Fi's. Only consider one of the Fi's in each iteration. In each iteration of gradient descent, let's not compute the whole thing here. Let's only consider one of them. And how do we choose that one? Randomly. Randomly we sample it. And if we sample it with replacement, so we can sample from a bunch of points, or a bunch of from a set, you can sample either with replacement or without replacement. Sampling without replacement is called bootstrapping in statistics. If you sample if you sample without replacement, it's called simple random. Sorry, if you sample with replacement, yes, it's called bootstrapping. If you sample without replacement, it's simple random sampling. Okay, so either with replacement or without replacement. Usually without replacement. That's why I have written bootstrap here. You sample one of the FIs and you do one step of gradient descent. This is called a stochastic gradient descent. As you see, it's different from gradient descent. Why? Because you have sampled FI. It's not the whole gradient. You have sampled one of them. Rather than this, you are using this. A stochastic, so approximation, the idea of a stochastic approximation was first proposed in 1951. You can see how old these are. It was first used in machine learning in 1998. And equation 33, as you can see, it has an adaptive step size. So we can have adaptive step size. And the step size can be, usually is decreasing. Why? Because we usually start with a large step size, because initially we assume you are very far away from the optimal point, optimal solution. But when we get closer to the optimal solution, we usually reduce the step size, because we know that when we get closer to that, we don't need to jump. We need to update step by very slowly, small amount. That's why eta k is usually a decreasing function by k. K is iteration index, like 1 over k, like 1 over second root of k. Or it can be not adaptive. It can be a fixed step size. Although it's not ideal, but we might have also a fixed step size, which is eta in all iterations. We usually have adaptive step size in stochastic gradient methods. Okay, now let's talk about the convergence rate of the stochastic gradient descent. Okay, again, assume the function is a summation of FIs. And it is bounded below. What does it mean? Bounded below, it means it doesn't go to minus infinity. There is a lower bound for the function. It doesn't go to minus infinity. And each FI is also differentiable. Therefore, the F itself is also differentiable, because it's a summation of differentiable functions. Let the function F be, the domain of it be D, okay? And let its gradient be L smooth. Again, at the equation 2 that we had in the first slide. Okay. And assume that what does this mean? These are the assumptions. But I haven't brought the proof. If you see the proof, you'll see that this assumption is used in the proof. It says that let the expectation is nothing but by mean. It's mean. You know mean. Mean in some specific distributions like Gaussian distribution is equivalent to average. You can see it as average or mean. The mean of sec squared L2 norm of gradient of f conditioned on xk. It means that if you know xk, the mean of this term is less than or equal to beta squared. So it is bounded from above. That doesn't matter. If you don't understand that, doesn't matter. Just for the sake of completeness of this theorem, I have put it here. Okay. Depending on the step size, what is important here to understand is our equations 35, 36, and 37. Here it says that if the step size at iteration k is 1 over k, the convergence rate, I mean how fast we get close to the optimal solution, is of order of 1 over log of t. First, you might be wondering why we are talking about convergence rates, because if you see in the literature of optimization, especially for first order optimization, they usually talk about convergence rate. So whenever someone proposes a first order optimization method, they usually talk about convergence rate. This is an important piece of papers on the first order optimization. So order of 1 over log of t. If eta k is 1 over second root of k, the convergence rate will be log of t over second root of t. If it is fixed step size, it will be 1 over t plus eta. Now let's discuss this, what these mean. Okay, first off, from between these two, which one is faster? I don't know. We should draw these functions. I haven't drawn this, but we can draw that 1 over log of t and log of t over second root of t and see which one grows faster. Whichever grows faster, it means that one is has faster convergence. However, I want you to notice equation 37. When we have a fixed step size, it means that, do you remember this was the gap between f and f star, right? Because f minus f star was less than or equal to this term. It means that by the end, we never reach to the optimal solution. We always have a gap of eta between us and optimal solution in the convergence. Why? Because it's obvious. Because when we get closer to this solution, if we don't decrease our learning rate, we always jump around the optimal solution. So assume I'm very close to the optimal solution. Rather than moving a little to reach it, I jump over it and I go to the other side of it. Then I come back again. So I jump back and forth around the optimal solution with the distance eta, with this distance. That's why when you tend t to infinity, it means that if you have infinite number of iterations, this term becomes 0 almost, plus eta. It means that you have always some eta oscillation around the optimal solution. That's why it's better to use adaptive learning rate. But if you have adaptive learning rate, of course, when you tend k or t, k and t are the same thing here, used interchangeably. It means iteration index. When you tend k or t to infinity, the learning rate becomes 0. It means that at the after infinite number of iterations, you don't update anymore because you are already on the optimal solution, right? So that's why the gap here becomes 0 at the end. If you tend t to infinity, these become 0. Okay. Now, if fi's are strongly convex, mu strongly convex, recall preliminaries that we talked about, then the learning rates change. Sorry, the convergence rates change in this way. If eta k is 1 over mu k, mu is the mu strongly convex, then the convergence rate is 1 over t. If it's fixed, again, we have some eta term here because we always will oscillate at the optimal solution, right? Okay, so we had these, and the explanations that I told you are here. So one thing which I want you to note is that for convex, we saw it here. For convex, equation 37, when we have fixed step size, is 1 over t plus eta. For strongly convex is equation 39. I have repeated them here, right? Now let's compare these two. It means that as strongly convex is easier to optimize, you can see it's much faster. It's exponential. It's exponential. However, here we have we don't have as we are not as fast as this. It's much faster. If you tend t to infinity, you will see that this grows much faster. Why? Because obviously, because strongly convex is easier to optimize. That's another thing I wanted you to understand. Any questions so far? No? Okay. By the way, guys, these are important algorithms that you will hear a lot in optimization, in machine learning, and also in optimization itself. So please listen to me and try to understand carefully. If there is any question, ask me. Okay, now we talked about stochastic gradient descent. Now we are going to talk about mini batch stochastic gradient descent. Usually, sometimes in the literature they are used interchangeably, but mini batch stochastic gradient descent is different from stochastic gradient descent. Sometimes people, when they say stochastic gradient descent, they mean mini batch stochastic gradient descent. And what is this? It means that, do you remember in SGD, SGD is short for stochastic gradient descent. In SGD, we had sampling one of the FIs in each iteration. So when we sample one of the FIs, by the way, guys, here also in SGD, when we sample one of the FIs, we are not very accurate. Why? Because we are not considering the whole gradient. Do you remember the whole gradient? We are not considering it. In also, I want you to note one more thing here because it's important. Do you remember in gradient descent? In gradient descent, let me bring it here. Where was that? No. In gradient descent, equation 29, the convergence rate was 1/t regardless of the step size, eta, right? It means that even if you choose a step size to be constant, you will reach to the optimal solution. Do you know why? You might be wondering why. If I don't change the step size and I have it fixed, again, as I explained, you will have oscillation at the last iteration around this solution, optimal solution. But here in equation 29, for gradient descent, not a stochastic gradient descent, for gradient descent, we are 1/t regardless of eta. It means that at after a lot of iterations, we actually reach to the optimal solution without any gap. Do you know why? Do you know why? The reason is that your gradient becomes almost zero. So what was the update step for gradient descent, which was minus eta gradient of f, right? This eta, assume it is fixed. Okay, even if it is eta is big, if your gradient of f becomes very small, because at the optimal solution, you know that the gradient exactly at the optimal solution is 0, and close to it is close to 0, right? So the update will be very small already. So when you have gradient descent, when you consider the full gradient, you don't have the problem of oscillation at the end, even if you use a fixed step size. But there is a but here. In stochastic gradient descent, the problem of oscillation by eta happens. Do you know why? Because even close to the optimal solution, your gradient is not accurate. You're just sampling one of the points. Therefore, your gradient doesn't become small enough that you might oscillate after many iterations close around the optimal solution. Therefore, it means that, in a nutshell, in summary, it means that a stochastic gradient descent is less accurate than gradient descent. And it's obvious why. Because it's approximating the gradient by sampling, right? It's stochastically approximating the gradient. Okay, so stochastic gradient descent has a problem, but what is the benefit of a stochastic gradient descent compared to gradient descent? If it's less accurate than gradient descent, why do we use that? There is a reason. Again, why did we start SGD? Because we said calculation of the full gradient is time consuming and it's hard, especially when we have a lot of FIs. So these are the pros and cons. Pros of stochastic SGD is its fast calculation of gradient. At every step, we are faster. At every step, our calculation is faster and easier. But the total thing, until convergence, is very slow. And also, at the end, it's less accurate. So pros, at every step, it's easier to calculate. Cons, at the end, it's less accurate. Okay, so gradient descent also has its pros and cons. It's accurate, but it's time consuming. So we need some middle case to be not bad as SGD and not bad as gradient descent. And the middle case is called mini batch stochastic gradient descent. It says that rather, let's not calculate the whole full gradient as in the gradient descent, and let's not sample one of the FIs as in SGD. Let's group them and sample a group of them, a batch of them. Batch is the name for the group. Let's have a batch of them and sample the batch. Okay, and this batch is called mini batch usually. It's mini batch SGD or hybrid deterministic stochastic gradient method. So these batches are usually, their union becomes the whole data set, but they usually don't have intersection. So you might have different algorithms, different variants of mini batch SGD. Someone might say, okay, I want to have overlapping batches, but usually batches, you divide your whole data set into several non-overlapping batches to cover the whole data set. Okay, N is the number of FIs or points, and B is the batch size. Okay, so it's a middle case. It's it's more accurate than SGD, less accurate than gradient descent, but it's also easier and faster to calculate gradient compared to gradient descent. So it has both advantages, the advantages of both worlds together. Okay, and you can see here it's similar to gradient descent, but rather than summation over all i's, we'll have summation over all points in the batch only. So this, and mini batch SGD is mostly used in used a lot in neural networks. You can see the interesting results of the AI that you can see nowadays. They are optimized by mini batch SGD or another algorithm, which we will see soon. Okay, and what is epoch, by the way? Epoch, so as I said, when you have your whole data, when you have your whole data, you divide it to several batches, right? Several mini batches, and they usually don't have intersection. Their union should become the whole data set, right? So you usually go one by one batch, and then you go to the next iteration, the next batch, and then the next batch. When you cover the whole data by going over all batches, that's an epoch. Epoch covers the whole data once. Then you continue with the first batch again. So first batch, second batch, third batch until the end, one epoch, you go to the second epoch. You start with the first batch again. You also might shuffle the batches. So, but at the end, in each epoch, you need to cover the whole data. That's called epoch. Okay. And you go until several epochs until convergence. You get close to your solution. Any questions so far? No? Okay. Now, we already talked about the convergence rate of gradient descent, as well as SGD. Now let's talk about convergence rate for mini batch SGD, which was the middle case, right? Middle case scenario. Okay, again, with some assumptions that we talked about, bounded below, differentiable, and the gradient be L smooth. Let the step size be fixed, eta. Okay, one important thing, you can see that when you have the average of gradients over the batch, so you are approximating the full gradient. In SGD, you are approximating the full gradient by gradient of Fi only, which is a very terrible approximation, but it's fast. In mini batch SGD, you're approximating the full gradient by the mean of gradient over the batch only. Okay, of course, you will have some error. Here, ET is the error in that iteration. Okay, if ET is the error, the convergence rate of mini batch SGD will be 1/t plus this error. Well, what does it mean? It means that whatever error you have, at the end, you will have that error of oscillation around the optimal solution. So if your batches represent the whole gradient very well, your error is small and you will reach to an optimal solution. However, if your batches are terrible approximation of the full gradient, you will oscillate a lot around the optimal solution at the end. Increase t to infinity and you will see. Okay, So, and if it is strongly convex, you will have this. Again, as expected, strongly convex is faster because it's easier. It's exponential here with respect to t. So, okay, one interesting thing here is that if you enlarge your batch to cover, consider the extreme case. Assume your batch is very, very large, that it is the whole data itself. So if your batch size is n, b equals n, it means that you will have only one batch which covers the whole data. Then this e will be 0. Of course it will be 0 because f was summation of fi's, right? If your bi is bt, which is the batch, the whole data, gradient of f is 1 over n sigma over I, the gradient of fi. This is exact full gradient. It means that the error will be 0. It means that, of course, you will be very accurate because your mini batch SGD will reduce to gradient descent. You will get the convergence rate of gradient descent. This is a sanity check for equation 44. If ET is 0, because if you you increase batch to become the gradient descent, then you will get a convergence rate for the gradient descent. Okay. So this is the middle case scenario, which is used a lot in AI. Okay, another thing. If we sample batches, so we can, do you remember I said we have batches next to each other? You're usually non-overlapping, and the reunion is usually the whole data. But now let's consider other variants. Let's consider that we are sampling batches rather than making them like this without any overlap. Let's sample batches. They might have overlap, they might not have overlap, but what I want to say that let's sample batches with replacement or without replacement. Without replacement, simple random sampling. With replacement is called bootstrapping. Okay, you will see that when you do sample batches without replacement, your error, expectation of your error, the mean error, squared error that we talked about, is equation 46. And if you sample with replacement, your error becomes equation 47. For proof, look at our tutorial. I have written a tutorial about its name is sampling algorithms from survey sampling to Monte Carlo methods. This is reference 18. You can see the proof there. But let's discuss these equations and analyze them. What do they mean actually? It means that when you are sampling without replacement, if you increase b to become n, it means that your batch size becomes n. This error becomes 0 because b is n, 1 over n becomes 1, 1 minus 1. This parenthesis becomes 0. So this error becomes 0. Exactly the explanation that I said in several minutes ago. I said if consider the extreme case that you are increasing the batch size. But this doesn't happen when you are sampling with replacement. Do you know why? Because when you have a bunch of batches, when you have with replacement, you might sample the same batch back and forth. Subsequently, you might sample it again. You might sample the same batch. You might sample the same batch. Okay, so it doesn't mean that their equations for errors will be different. But now I think you can guess, as you see in equation 47, what should we do for this to for this error to be 0 when we are sampling with replacement? You need to increase b to infinity. It means that if you increase the batch size to become infinity, then even with replacement, your error becomes 0. I think now, if you think about these two equations, you will understand what I'm talking about. Again, you can have, usually we have sampling batches without replacement, especially in AI. Okay. Now, if you have any question, please let me know. No? Okay. Another group of methods named Stochastic Average Gradient method. Okay. Stochastic Average Gradient, or SAG, it was proposed in 2012. As you see, we are getting closer and closer to the state of the art. We started from the previous century. Now we are getting closer and closer to the state of the art algorithms in first order optimization. 2012 is not very far away. Okay. It says that let's keep a trade-off between accuracy and speed. You remember accuracy, speed of SGD methods were high, but their accuracy was low. The speed of gradient descent was low, but its accuracy was high. SAG says let's have a trade-off between them. Again, a middle case scenario. How do we do that? Similar to what a stochastic gradient method was doing. It says that, look at this. What is this? This is gradient descent. When we have Fi as the summation of Fi's. This is the full gradient, this term that I'm circling. This full term is the full gradient because it's the mean of gradients. And this is a gradient descent. What does SAG do? SAG says, let's randomly sample one of the points. So its idea here is like SGD, right? Let's randomly sample one of the points, but update its gradient among the gradient terms. So what here is the difference from SGD. In SGD, we say, let's sample one of the points and use its gradient only. SAG says, no, let's sample one of the points, update the full gradient, update its gradient in the full gradient. So consider the full gradient, summation of gradient of Fi in the previous step, the full gradient in the previous step, minus the full gradient of this point in the previous step. So you have the full gradient in the previous step, you take the part of the gradient in the previous step of that point, and you replace it with its gradient in the current point, in the current iteration. So you take away its gradient in the previous step, and you replace it with its gradient in the current step. This is what SAG does, and you see its difference from SGD. Okay. Its convergence rate is 1 over T. Interestingly, it has used similar idea to SGD, but it's as accurate as gradient descent. So it has both a speed and accuracy together. Okay, you might be wondering, if SAG is so successful in both speed and accuracy, why isn't it widely used nowadays, especially in machine learning, AI, and these things? There is a reason, because practical experiments have shown that SAG requires a lot of parameter tuning. For example, you need to do a lot of tuning for your specific data set for it to outperform other algorithms. That's what are the parameters? For example, eta. You need to find which function of which decreasing function should I choose, or what step size should I choose for this to work well, perfectly well. Empirically, people have seen that. Also, as you see, SAG has the same rate as gradient descent. Although in practice, they have seen that it usually needs some more iterations. Although in theory, it has the same convergence rate, but in practice, it's usually a bit slower than gradient descent to converge. Now you see, sometimes theory and practice don't match completely. Here is an example. Okay. Any question? No? Now, we are in the stochastic variance reduced gradient method, or SVRG. It was proposed in 2013, a bit closer to us. It's the same as SAG. So it's an improvement over SAG. But for every iteration, it updates the solution m times. So it puts this update that we had in equation 48 in a for loop. And it does it for m times. It says like, okay, at every iteration, I'm updating, let me update several times. Apparently it works better. Okay, SVRG is an efficient method. Its convergence rate is also, it can be proved that it's similar to SAG. Both SAG and SVRG reduce the variance of solution. So usually don't have a lot of variance in your final solution. However, again, in practice, they have seen that they are using gradient descent because that's easier. Okay, now let's talk about adaptive learning rates. Eta, let's make it adaptive. There are several algorithms specifically for adaptive learning rate. Okay, because up to now, our adaptive learning rates were just some decreasing functions like 1 over k, 1 over second root of k or something like that. But now let's propose an algorithm which actually calculates the good eta at each iteration. And there are some algorithms for that. Let's look at them. Three most well-known algorithms for adaptive learning rate are AdaGrad, RMSProp, and ADAM. I think the people who already know machine learning or AI a bit, they have heard of ADAM a lot. ADAM is one of the most used optimizers in neural networks and deep learning. And we'll see them. We'll see all of these. You might be wondering why I'm talking about machine learning a lot. I'm not talking about machine learning. I'm talking about optimization. These are optimization algorithms. They are used a lot in machine learning. Okay. Because as I said initially in the course, machine learning is nothing but optimization and some statistics and linear algebra. Machine learning is that, nothing else. Okay. AdaGrad, short for adaptive gradient. We can, as I said, we can adapt the learning rate of stochastic gradient methods. AdaGrad or adaptive gradient, it was proposed in 2011, as you see, close to us. It updates the solution iteratively as this, equation 49. Look at the iteration 49. So it's very similar to gradient descent, but it has inverse of G. G is the matrix. Inverse of G here before the gradient. Gradient is a vector. G, inverse of G is a matrix. Matrix times the vector becomes a vector, right? G is a diagonal matrix, D by D. D is a dimension of data, the dimension of X, right? And so diagonal matrix means that the off-diagonal elements are 0. The element JJ, the JJ element in this matrix G is this. And let's talk about this. First off, what is this eta, or sorry, this epsilon? Epsilon is greater than or equal to 0. They put it for stability. They want to make G full rank. Why? Because you want to take inverse of G. Therefore, G needs to be full rank. If you don't know what full rank means, these are you don't need to worry about this. You can look them up later. But when you have a matrix, the rank of the matrix should be full for it to be invertible. In other words, it shouldn't be singular. Okay. For this to be full rank, we can, one way to make a matrix full rank is strengthening its diagonal. So when you have a matrix and you have doubt whether it's full rank or not, you can add some epsilon I. I is the identity matrix, diagonal matrix. Epsilon I to it. It means that you are adding some small value to its main diagonal. It will probably become full rank. It means it becomes invertible. Okay, you won't get error in your code, because if it's not full rank, you will get error in your code. Okay, so, and what is IT? IT is some randomly sampled point from 1 to n at iteration t. So t, tau or t, whatever here it is the iteration index from 0 to k. K is a current iteration index. Okay, so and you at each iteration you are having one of the points, you're sampling one of the points randomly, similar to the idea of SGD. And also, what is this? It's the gradient of fi tau. So fi tau, because we had fi's, right? Now let's take the I tau of them. I mean I tau, the I teeth of them. Let's take that. So let's take the one of the fi's randomly, in other words, and let's take the derivative of that. And that derivative is a vector, right? Let's take the jth element of that. Let's take the jth element of this derivative. And this is this. And let's square it because it's a scalar, right? And then we sum over these because we in each iteration from 0 to k, we have one of them. And this is g. You put it here. If you replace this equation 50 in equation 49, it will give you equation 51. Very similar, as you see, to gradient descent, but with some difference here. We have this fraction. Okay, what is it doing? Let's interpret what it is doing. It is keeping a history of sampled points because as I said, in each iteration you're sampling one of the points, similar to stochastic approaches algorithms. So we are keeping a history of them because we are summing over all of them from the iteration 0 until now. It takes derivative for them. It is taking derivative for them, yes, to use. But during the iteration so far, this is the summation over the iteration so far, right? If a dimension has changed significantly, it means that if this derivative is high, it means what is derivative? Derivative means change, right? Yeah, right? So derivative is the rate of change. When the derivative is high, it means that its change is huge. If this term is high, it means that this dimension has changed a lot. It means that, but now it is in the denominator. It means that if a dimension has changed a lot, you should dampen, you should reduce its update size. So the learning rate of the dimensions which have changed a lot should be decreased. In other words, in simple words, it says, do your gradient descent. However, if you have changed one of the dimensions a lot, don't change it anymore. Let other dimensions change too. So you have a uniform change, kind of a uniform change between all of the dimensions. In other words, give chance to all dimensions. Do you get it? Give chance to all dimensions to change. Don't change only one of the dimensions. Don't kind of, in the machine learning language, don't overfit to one of the dimensions. Change all, give chance to all of your dimensions. This is the idea of AdaGrad. Another algorithm for adaptive learning rate is root mean square propagation, or RMSProp. It was proposed in 2012. And it is an unpublished paper. It was, I think, a slide deck by Hinton. And it is an improved version of PRProp, resilient backpropagation, which was proposed in 1992. And this RProp was using, so this algorithm uses the sign of gradient in optimization. Okay, now let's see what it is. Inspired by momentum. Do you remember the momentum term that we had here? We started this session by momentum. Inspired by this, it updates a scalar variable v as this. So what is this? We are defining a variable, a scalar variable v, and we are saying that updated by this, a linear combination of previous V in the previous step. Gamma is some number between 0 and 1, right? So it's a linear combination of the previous V and the derivative of the gradient at the previous solution, but it's a squared L2 norm. So this is equation 52. Usually gamma is a large number, but close to 1. It's a forgetting factor. And what does it mean? Let's talk about it. Assume it's 0.9. It means that don't forget the previous V a lot and use the gradient in the current solution by 1 minus 0.9, which is 0.1. So it says that because, as you remember, consider this here, equation 53 is very similar to what we have in equation 51 in AdaGrad. Look at them, compare them. I go back and forth so you can compare them. So we are replacing this with V. And what is V? V is defined here. It's a linear combination of V and gradient, right? Here we had, in equation 51, we had gradient of F. Here we also have gradient of F. Here we also have gradient of F, but plus the previous V. So it's also making a history of the previous V, similar. So it's kind of, I can say it's a combination of ideas of momentum and AdaGrad. AdaGrad idea plus the momentum idea becomes RMSProp idea, right? Very similar, interesting. And they are working well. They were working well in neural networks, in optimization of neural networks. The most well-known and successful algorithm for adaptive learning rate is ADAM, short for adaptive moment estimation. ADAM optimizer improves over RMSProp. So RMSProp that we talked about here, it was itself a combination of ideas of momentum and AdaGrad. Then it was improved later to become ADAM optimizer. And I remember ADAM optimizer was proposed close to us less than 10 years ago. I don't remember the exact year, but it says that, okay, improves RMSProp by adding a momentum term. Again, you might say, okay, you had momentum in RMSProp. No, we didn't have momentum. We had the idea of momentum. So we had the idea of history that we had in momentum in V in the AdaGrad. However, we didn't have an actual momentum. ADAM optimizer says let's have an actual momentum similar to that in a way that here you will see that. Okay, consider equation 54 and 55. 55 we have it from the prop RMSProp. Nothing changes much. 54 is a M. I think you can see maybe standing for momentum, whatever. Naming is not important. A vector M is a linear combination of the previous M and the gradient itself. See, there is a difference between V and M. V is a scalar, and also it's considering the length of the gradient, the squared length of the gradient. M is considering the gradient itself, not the length of it. Okay, and we have gamma 1 and gamma 2 because we have two variables now. Okay, now we kind of normalize them, M hat and V hat, in this way. This is just normalization, and we put them in the famous equation of 53 or 51, right? As you see, all of these three algorithms are very closely related, and this becomes ADAM. So ADAM, that so far you might have heard of ADAM, and you say, oh, you might have wondering, what is ADAM? Why do people use ADAM a lot? And you see, it's not very complicated. It's just an adaptive learning rate. It's adapting the learning rate in gradient descent. And why is it not using neural network? Because backpropagation is nothing but gradient descent and chain rule. Now they use ADAM for adapting its learning rate. That's it. Okay. Any questions so far? Guys, can you give me some feedback? Can you please give me some feedback? Are you listening to me? Hello? Okay. So in the chat, all good so far. It is clear for now. Okay, great. So yeah, please let me know if there is any question. Let me continue. Okay, coding a neural network. So here, let's code a neural network. I have put it here. I wanted to annotate them, but now that I can't annotate them, let's go to the actual code that I have in the Jupyter notebook. Let me share my, yeah, I think I need to share my, give me a second. Can you see the code?
Yep.
Okay, great. So you can code your Python code either in a .py file or in a Jupyter notebook file. I think it's .ipynb, something like that. And Jupyter notebook, you can install Anaconda, and through that you can have Jupyter notebook, or you can use different platforms such as Google Colab for running and coding in Google, coding your Jupyter notebook. Okay, what is Jupyter notebook? It's blocks of Python code. So if you are familiar with MATLAB, it's similar to what you have in command line of MATLAB, but the .m file of the MATLAB is the .py. But what you want to try very fast, some things you want to try them fast and block by block, then you can do it in Jupyter notebook. So here I'm running this. So what is this? Pip is for installing the packages. When you have some packages in Python, you usually use pip or conda. So usually by default people use conda, and if conda doesn't work, they usually use pip. So try first, after installing Anaconda and these things, try conda and then pip. But if you are using Google Colab, it's the other way around. Usually you use pip, and if it doesn't work, then you use conda, because pip usually is the default thing for the Google Colab and these things. So I'm gonna install Torch. So we have several libraries for neural networks, for coding neural networks. One of them is PyTorch or Torch. One of them is TensorFlow. These are the two well-known libraries nowadays for the neural networks. We have some almost outdated libraries for neural networks, such as Keras. Keras was also related to TensorFlow. Another one was what was it? I have forgotten some of their names. What was it? If you remember, please let me know. I don't remember for now. But there were several algorithms, libraries. Scikit-learn is for usually non-deep learning machine learning. So scikit-learn is no. PyTorch, I said that. So PyTorch and TensorFlow are the most well-known ones right now. So they are developed by two big companies, TensorFlow by Google and PyTorch, I guess, by Facebook. I'm not sure about it. Yes. So I believe PyTorch is easier. because it's very more similar to NumPy and Python, actual Python. TensorFlow is a bit tricky. Now let's install PyTorch. I just shift enter it. Shift enter runs the cell. So it is installing Torch in my Google Colab session. Yeah, I think it already installed that. Yes. Now I'm importing my packages or libraries. So if you are familiar with C, you import your libraries by include. Do you remember hashtag include? In Python, you import by import, not include. Import torch, so I'm importing the torch library. Also, torch.nn means that from torch, you have maybe a class NN, standing for neural network. Import it, but rename it as NN. I want to call it by NN. Also, we say from torch library, there is a package. So from the package torch, there is a class or a package utils, or usually it's a path, a folder. So when you have a package torch, you have a folder in it, utils. In the utils folder, you might have a data.py. So then you say from torch.utils.data. It means that from that data.py inside the utils folder in the torch package, import. There are two classes apparently in the data.py. One of them is data loader and the other one is dataset. And what do I mean by class? In parentheses, let me briefly tell you what class means. So class is in programming, you might not know that. So in object-oriented programming, we are saying that I think the best example for us to understand classes and object-oriented programming is that assume you have some concepts. I think the best thing which explains that is the ideas of Plato in philosophy. Have you heard of that? The ideas world of the Plato in philosophy. So Plato, it says that every object in this world, everything in this world has an actual essence is another spiritual world, and that's called the idea. So we have an idea of human, but Benyamin, me, is an illustration of that idea, is an object of that idea. So each of you is an object or an instance, let's say instance of that idea in the spiritual world. This is what Plato says in ancient Greece. We might have the idea of rooster. We might have idea of any living being, right? So we have different ideas, which is the ideal case for that thing, but we have instances of that on the earth. This is in philosophy, the ideas of Plato. You can look it up. Now let's use that for explanation of object-oriented programming. We have some concepts like ideas of Plato, and then we have some instances of that concept. We usually store this concept in the hard drive of our computer, in some part of the computer, in the storage of our computer. And then in our RAM, for example, we say, okay, we instantiate that concept and bring it into the RAM. So we have some idea or some concept of, for example, human in the hard drive. Then I say, okay, I want to instantiate that and make Benyamin, which is a human, in my RAM. I may make another one named John, whatever. And when I'm instantiating them, I give them attributes. So each idea or concept in the storage has some attributes. And then when we are instantiating them, we set those attributes. For example, human might have the attributes eye color, height, width, weight, whatever. And when I'm instantiating that, I say, okay, Benyamin, eye color brown or whatever, hair color black. These are the statistics or characteristics of Benyamin in this instance. And also each concept or has some functions. For example, for human, one function is eating, one function is speaking, one function is walking, right? These have some functions. These functions are usually called method, especially in Java. These are called method. So when I instantiate that in my RAM, then I can call those functions of that instance. So for example, I say Benyamin, now talk. Then Benyamin starts calling the function talk, right? By the way, when I was instantiating that, I said I'm setting the attributes. Setting those attributes is done in a function, a specific function named constructor. Why? Because I'm constructing that instance in the RAM, right? So we have a constructor method. We have also some regular methods or functions. We have some attributes. We have that concept. That concept is called class in the hard drive. I also instantiate them in the RAM. Those are called objects. That's why we call it object-oriented programming. These are objects or instances. So this is the whole idea of object-oriented programming in 5 minutes, inspired by the ideas of Plato in philosophy. I think it's the best explanation for object-oriented programming. So dataset and data loader are two classes. Now I close the parentheses. So these two are the classes in this data.py. And what are they? These are the classes in Torch for loading the dataset, because you have some dataset, yes? You need to load them to feed them into the neural network. You also have this. What is this? It's a matplotlib. This is a library for plotting in Python. We also have NumPy. Import NumPy as NP. When we say as, it means that I want to rename it. I don't want to write NumPy, it's too long. I want to rename it to NP. Whenever I say NP, you see it as NumPy. And what is that? It's usually for working with arrays, right? So when you want to define vectors or matrices and these things, you need NumPy. And this TQDM, you can call it taqaddum. Why is it called taqaddum? Because in Arabic, taqaddum means progress, and many of its developers were Arabs. Taqaddum, so you want to show the progress of your for loop, how much time is left for it to be completed. When you have a lot of loops, then you can use taqaddum. It shows some progress bar on your terminal. And also, why do you use it here? Because do you remember I talked about epochs and batches, mini batches. So you want to see when your epoch is over. And you go to the next epoch. So the number of epochs can be the progress of the neural network. So now so we import them. Now let's define the network. So here we say device. If we have GPU on our machine, we use CUDA. Otherwise, we use CPU, right? Why do we can use GPU? Because in neural networks, usually you can do a lot of parallelization. Because you can feed several batches maybe together or something. You have a lot of ways to make it parallel. That's why you can use GPU to accelerate training. Now, define the structure of neural network. Let's define that. So we have, again, class. I already talked about what class means. So I define a class named neural network. It inherits from n.module, n neural network in Torch .module. And what is inheritance? It means that, for example, do you remember I talked about human? So I might have several classes. One of the classes is human. One of the classes is maybe animal, let's call it animal. Another class is monkey, another class is rooster or something. Human, monkey, rooster, all of these inherit from the class animal because all of them are animals, right? So you can say that they inherit some part. For example, the way that we give birth is a categorization of the animals, right? So we inherit giving birth from the class animal. But we have our own specific attributes too. For example, we can talk, but maybe the animals can't talk. So we have our own characteristics, but we inherit some from the class above us. So here we are also saying that let's have the class neural network, let's inherit its functions and attributes, but we'll also add some new attributes to it. And what are they? It says that I have layer 1, layer 2, layer 3, layer 4. So it's a neural network with 4 layers. And n.linear means that it's a linear or a feed-forward layer. It goes from 1 neuron to 10 neurons. The second layer goes from 10 neurons to 20, third 20 to 10. The fourth layer goes from 10 neurons to 1. So it means that the neural network starts from 1 neuron and it ends to 1 neuron. It goes up, it enlarges and goes down again. And we also have some activation functions named ReLU. You can look up ReLU. It's like this. If you look at my hand, it's like this. It's a nonlinear activation function. We already talked about activation functions in this session. So we have activation functions between the layers. So I'm getting this is the method forward in this class. It gets the input X, passes it to the layer 1, then from the ReLU 1, gets it, feeds this to layer 2 again, then ReLU 2 gets it, feeds it to layer 3, then ReLU 3 gets it, feeds it to layer 4 without any activation function, outputs it. It means that the last layer doesn't have any activation function, or it has a linear activation function. Why do I do that? Why don't I put any activation function in the last layer? Because I want to do regression. Usually in regression, we can say if you don't have any bound on your data, you don't set any activation function. But if you know that, for example, your data is between 0 and 1, then you can, for example, use sigmoid to bound the output to become between 0 and 1. So I run it. This is now I made this in the hard or a part of a RAM. Now I'm gonna instantiate that later. So here in this block, I'm gonna instantiate this class and name it net. For example, neural network is human, net is Benyamin. Okay. Now print net. You can see these are the attributes of this object. Now optimizer. We can usually 2 optimizers are very well known in machine learning, in deep learning. One of them is SGD. We talked about it, Stochastic Gradient Descent. One of them is ADAM. We also talked about it. Let's use ADAM. So we have initial learning rate, and then ADAM adapts that, right? LR stands for learning rate. We also, here we are defining the loss function. This is mean squared error loss. Mean squared error, I think you know that. It means that take the difference, square it, and then take the average mean. Okay, why do I use mean squared error loss? You should choose your loss wisely because I want to do regression here. MSE is a good loss for regression. You might have other losses like mean absolute error and other loss functions. Here I'm using this. If you are doing classification, you should use other loss functions such as cross entropy or others. Now here I have the class data. In class data, I'm reshaping my data to become vectorized and become a column vector. This is a NumPy vector. I need to make it a torch vector. And then I'll also cast it to float. I want it to be float. Even if the input is integer, it needs to be float for it to be understandable by the network. So I have data and I have label. And len, it means that when I have this instance of this class, when I say len of that, what should it return to me? I say, PyTorch, you need to return the length of the data for me. You can return anything else. You need to define it here. Get item means that, okay, when I have in this object, I say, for example, I have this object, I say, give me the first element. What should I return? It is asking me. I say PyTorch, return that item of data, also that item of label, concatenate them, give them as a tuple. So the first one should be point in that data point in that item. The second one should be the label of that point in that item. So I define that. Now I'm talking about data loader now. So I have, I may go a few minutes after the, over the class. I apologize for that, but let it be completed. I think it's worthy. Is that okay? Guys, is that okay? If I go a few minutes after over the class? Okay, you are not saying anything. Yeah, okay. So thank you. So this is the, okay, now we have batch size, mini batch size. Do you remember? We talked about the stochastic gradient, mini batch stochastic gradient descent. So we have some batch size B. We called it, denoted it by B in the slides. We set it to 16. Usually we put it to be one of the powers of 2, usually 16, 32, something like that. And it shouldn't be very large. Usually 32, 16 are good. And then we define the load data set, some function. It gets x train, y train, x test, y test. And then we say, okay, data, we have data. Do you remember? We defined the data class here, which was inheriting from the data set of the torch. We say data, we get x train and y train, we pass it to that. So it gives us a data, maybe DS stands for data structure, whatever, doesn't matter, train data structure. We should pass it to data loader, which was a class in the torch. Do you remember that? We imported that in the libraries. We pass it to the data loader. We give the batch size. We say, okay, shuffle it. We say shuffle the data. We usually, for the training data set, we shuffle it. For the test, we usually don't shuffle it. We don't need to shuffle it. But for training, we want it to be shuffled, not to be sensitive to the order of data points. And we have the train loader. We'll also do the same for the test, but we set the shuffle to be false, and we get back the train loader and test loader. Okay, let's run it. Now here, let's see the data set. Okay, I have defined several data sets, linear data set. We can have linear data set or non-linear data set. For example, for linear data set, I have defined it to be like this. It's like a line. So these are the red ones are trained, the blue ones are test. I'm generating some random. It's almost linear. Its function is not linear, but it's almost linear in this range. But let's talk about non-linear data set. And you can see I'm plotting it using matplotlib. Okay, now we call the load dataset function that we defined here. Let's call it. It gives us the train loader and test loader. Now, how many epochs do I want to train? Let's let it be 1000. Do you remember one of the convergence criteria that we talked for gradient descent? It was in the previous session. One of the last slides in the previous session, we talked about convergence criteria. And with one of them was the maximum number of iterations. And here it is. We are using that criteria. We are saying that let's use a maximum 1000 iterations or epochs here. So here, epoch is a meta iteration. So in each epoch we have a lot of iterations. So we're saying that use 1,000 epochs, each of which has several iterations. And for epoch, I'm using taqaddum in order to see the progress on the terminal here like this. And range says that from 0 to this number of epochs, and it is a description of this taqaddum epochs. You can write it anything. I'm defining a list named loss list in epoch. So in each epoch, I have some loss, right? And then in each epoch, I should have a loop over the mini batches. Do you remember? So each epoch is going through the batches once to cover the whole data set, training data set. But the training data set has several mini batches. So we have a nested loop. We have this loop for the mini batches. And in each, so train loader gives us, whenever it's a generator in the Python. If you look at the generator, look it up. Whenever you call it, it gives you the next thing. So you can call the generator, gives you the next thing. So it gives you, each time it gives you data batch and label batch, and it's a step. So then you pass it to the device. It's either CPU or GPU. It gives you the data batch and label batch. Then you pass this data batch to the network. This is the instance of network object net from the class neural network that we defined above. It gives you the prediction of the neural network, output of the neural network. Then you give the prediction and the label to the loss function that you had. Usually by convention in PyTorch, prediction is the first input for the loss function. The actual label is the second one. It gives you the loss function. Then you cast the loss to the CPU. If it is in GPU, it needs to come to the CPU again. You detach it from the device. Then you get its item, because it might have, it is a vector of one element, so you get its element by item. Then you append to the list. I want to see the loss. And you also here, this is an important step in PyTorch. You need to zero the gradient in optimizer in each step, because it shouldn't accumulate the gradients. You zero grad for optimizer, otherwise it is wrong. Then you backpropagate the loss function. This is the backpropagation that we talked about using, and we set the ADAM optimizer for that backpropagation. So it's gradient descent plus chain rule plus the ADAM adaptive learning rate. Then we have one step of optimizer. So this is the setup of backpropagation. This is the actual update. So this is xk xk plus 1 equals xk plus delta x. This is the update in the gradient descent. And also you are appending the loss list in the losses. So you can draw the plot the losses, and you'll see it goes down usually. Usually in big data, you'll see it better. Here it oscillates because it's not a big data. And then if I run it, you can see you see the taqaddum or the progress bar. So by the way, in taqaddum, this is the number of iterations left, and this is the total number of iterations. This is the time which has passed or elapsed time, I think. This is the time which has been left to finish. And this is the number of the time per second in each iteration. Each iteration, how much on average it takes. So it's a good, so you can see, for example, when you are training big data, you can see, okay, maybe tomorrow you can estimate tomorrow at 2 p.m. My training will be over, something like that. So you run it and then you test it. Let's test it. So you have prediction list. In test, one important thing in test, so you say with torch.nograd. You shouldn't have gradients in the test phase. So test or evaluate. So in machine learning, you have train, validation, and test. Validation is used for parameter tuning. Training is used for training. and test set is used for test or evaluation. It's better in coding. It's better that you don't call test as test. It's better to call it eval or evaluation. Why? Because you might confuse the terminology test with the unit test that you have in programming. If you are a coder, you know what I'm talking about. In programming, you usually write unit tests for your codes. Unit test is different from tests in machine learning. That's why we usually call it eval or evaluation. Okay, it's an evaluation phase or test phase, whatever. And we say with no grad because it's a eval phase, not training phase. Then we have again test loader. We had here train loader here in this line. Now in this line we have test loader. We pass the data batch, which is the batch in the test data set, to the network. It gives us the prediction, and then we concat the prediction extended in the list in order to have the list, the whole list of predictions. Now we can draw the predictions, as you see here. And the blue ones are the actual test, and the green ones are the predictions. By the way, here in the data, we have one input and one output. This is output versus input. So for data, if this, for example, here in this point that my cursor is here, if this is the input, like about 4.5, the output is about minus 0.9, something like that, right? But its prediction is here. But you can see overall, it has learned the nonlinear pattern of the sine function here, the nonlinear function here. So it is working. It is working. We can also try it for linear data. Almost linear data. Let me run it again. And why is it so fast? Because it's a synthetic data set. When you have an actual data, it might take more time to train. Okay, now evaluation. Now let's visualize. As you see, it's almost learned the linear pattern of data. So this is regression. You can have any loss function you can have for classification, regression, clustering, and anything. You can use it for, as you see, it has a lot of applications in different areas of engineering and others. You can use it in for predictions. So this is coding of neural network. You can code it in other languages too. And I think, yes, any question? Is everything clear? Okay. So yes, people are saying it's clear. Great. Thank you very much. So if there's no other question, let's conclude the session. And thank you very much. Thanks. Have a good night.